Hello, we're going to do a few problems out of chapter 12. So I picked out 4, hopefully one from each of the more challenging ideas. So I'm going to plug in the camera. Okay, and share the screen. And I'll hopefully remember to move it up when we get to the bottom of this first problem. So the first problem is on page 484. So if you look at the problem, it'll be helpful for you. So it's one where you're going to determine the rate law. So they give you this reaction, nitrogen monoxide reacting with chlorine, and ask you for the rate law. So they give you a table of data where they've run 3 different experiments. And you notice that in some of the experiments, the concentration of nitrogen monoxide is the same. So that's 1 and 3. And then in 1 and 2, the concentration of Cl2 that they start with is the same. So that will allow us to say, if I want to know what the rate law is, I want to be able to say rate equals some constant times each of the reactants raised to some power, and I have to determine what that power is with these experiments. So if we look at experiment 1 and 2, where the chlorine is held constant, those 2 experiments will allow us to figure out the rate or the order with respect to nitrogen monoxide. So if I take a ratio of the rates, so if you look at experiment 2, the rate's 4 times 10 to the minus 2. The rate of 1 is 1 times 10 to the minus 2. So each of those has to be equal to K times the concentration of each species raised to its coefficient. So I put in the conditions that experiment 2 were run at and experiment 1. And then if you look at this ratio, provided you carry out the 2 experiments at the same temperature, the rate constant shouldn't change. And if you've held the chlorine concentration constant, it doesn't matter what y is, because 0.2 to the y and 0.2 to the y will cancel. And so you end up with the ratio of the rates, which is 4, is equal to the ratio of the concentrations of the nitrogen monoxide raised to the power of x. And in this case, the ratio of the concentrations is 2. So 2 to the x equals 4, and it's second order with respect to nitrogen monoxide. So then we have to figure out the order with respect to chlorine by picking 2 experiments where its concentration starts out at a different quantity, but the concentration of nitrogen monoxide is the same. And so we'll look at experiment 1 and 3. We'll set it up exactly the same. Rate equals K times each concentration raised to its power. And experiment 3, same thing. But now the K should be constant. The ratio of the nitrogen monoxide concentrations should be constant because the experiments had the same concentration. So we end up with 2, so 1 times 10 to the minus 2 divided by 5 times 10 to the minus 3 equals 2. And the ratio of the concentrations is 2. So 2 equals 2 to the y. Therefore, it's first order with respect to chlorine. So that's the rate law that you can figure out from that experimental data. So the other thing they want you to do in this problem, a couple things. They want you to just determine the rate constant. And I want you to make sure you could just set it up with 1 experiment. So if you start with the first experiment, the rate equals K times each concentration to its order. And you end up with a rate constant of 3. And the units are 1 over molarity times seconds. But really, because you're always going to have experimental error, you should calculate the rate constant for all 3 experiments. Your book, strangely enough, always ends up with perfect data. That's not going to happen to us in lab. But still, always calculate all 3 just in case, and then take an average. So the rate constant is 3, and then make sure you always include the units because rate constants have units. So for this third order reaction, we have 1 over molarity squared times seconds. And then the very last thing they ask you to do is what's the initial rate when the concentrations both start out at 0.12. So what's the rate when we know the rate constant? Each concentration starts out at 0.12. You just have to do the math on the right-hand side, and you end up with a rate, and I should have put in units, of 5.2 times 10 to the minus 3 molar per second. So the next problem we're going to do is one where you're going to use Excel. So look at problem 1259. 1259 wants you to use the following data to determine the order of the reaction and the value of the rate constant. So the data that they give you is for this reaction, NOBR, and they did an experiment where they monitored the concentration as it changed over time. So that tells you you're going to use the integrated rate laws. You know the concentration at several times. In the last experiments that we looked at for the previous problem, that was an initial rate problem where you were looking at how the rate changed when you change the initial concentration. This one, you're actually monitoring over time what happens to the concentration. So what you should do, so I'm going to pull up my Excel screen. And I think I'm going to stop sharing and then share again because I feel like every time I don't do that, it shouldn't be true, but it doesn't share properly. So if you look at this screen, I have 3 different sets of data. So the first one is time versus concentration. So if you look at the table on page, there's a table. On page 453. So on page 453, it tells you what to plot to determine if it's a straight line to determine the order. So for 0th order, it's concentration versus time. For first order, it is natural log of concentration versus time. And for second order, it's 1 over concentration versus time. So I've made all 3 of these graphs, and notice I've calculated a trend line, so a best fit line. If R square was 1, it would mean the line goes straight through your data points and it's perfect. So you want the R squared closest to 1. The one that is closest is, let me make this a little bigger for you. Too big, sorry. There we go. So you notice that when I graphed 1 over concentration versus time, the R squared is closest to 1. So that tells me it's a second order reaction. And the rate constant is the slope of that line. So it's the 0.7552. Okay, so it's second order because 1 over concentration versus time gives the R squared closest to 1. So it's the best fit to the data for a straight line. And the K is 0.7552. That was the slope of that line of 1 over concentration versus time. And make sure you always include units. So for a second order reaction, the units of K are 1 over time times concentration. Our time units were seconds. Whoops, that is a lie. I put up here that it's minutes. I better confirm which one it is. Whoops, this is wrong. This is in seconds. I copied the minutes from the problem in front of it. So these units are right. So that's one you really should be able to do. And on the test, you'll be able to use Excel. You'll also be able to use Wolfram Alpha, Mathematica. So when we meet together or you come to my office hour, if I can help you with any of those software packages, let me know. So the next problem is one that deals with radioactive decay. So a little bit blurry. Not too bad. I'll talk through all the numbers. So if you read problem 7 or 12.73, tells you you have a sample of magnesium that's radioactive. So it's the 28th isotope. And it has a decay rate when you first have the sample of 53,500 disintegrations per second or minute. So that means that many nuclei disintegrate per every minute. But then after 48 hours, that rate falls to 10,980 disintegrations per minute. And so the thing with radioactive decay is to realize, and you'll read the section in the book, that it's first order. It's always first order. So you know how to write the rate law. So the rate initial is equal to the rate constant times the number of nuclei that you start with. And when we finish this chapter, I guess I've already given the lecture on the chapter, you'll know that the rate constant doesn't ever change for radioactive decay. Changes for chemical reactions if you add a catalyst or you change the temperature, but it won't change for radioactive decay. It's a different process. So the initial rate is K times how many nuclei you start with. Then the rate will change to K, the same K, times the number of nuclei that you have at this new time, number 2. So what you'll notice from that is if you take a ratio of the rates, the rate constant will cancel, and the ratio of the rates is equal to the ratio of the number of nuclei that were present in those 2 experiments. And so if I put in the 2 rates that are given, the 53,500 and the 10,980, the ratio of the rates is 4.8725. That has 5 sig figs right here. And so that's also equal to the number of nuclei that are present in each of those experiments. So now because I know it's first order, I can use the natural log equation. So the natural log of the ratio of those concentrations is equal to K times T. So now I can put in 4.8725 for the ratio of the concentrations, put in the 48 hours and solve for K. So I got a K. Where did I put 1 over minutes? That K should be 1 over hour because I'm working in hours. So 3.30 times 10 to the minus 2, 1 over hours is the rate constant. And if you look back at that table on, I think was it page 453, the one that tells you about different ordered reactions and what you graph, it also tells you how you determine the half-life. So it says on page 453 in that table, which you could have on your note card, that the half-life is equal to 0.693 over the rate constant. So all I have to do is plug in my value for my rate constant, and I end up with 21 hours is the half-life for this particular reaction. So point of that, and the reason it's in this chapter, is radioactive decay is always first order. So you always would use, from page 453, the equations for a first order reaction. Okay, one more, and this is one dealing with mechanisms. So in 1285, take a look at that in your book. I think I've copied most of the information. It gives us these 3 steps in a mechanism. So they're proposing how the reaction takes place. So N2O5 goes to NO2 and NO3. NO2 and NO3 go on to form NO, NO2 and O2. The third step is NO plus NO3 goes to form 2 NO2s. So the first question they ask you is, if these are the steps I'm proposing, what's the overall reaction? So all I have to do is add them together. So in order to add them together, you have to realize that if the first one can go backwards, it really has to happen twice for the reaction to take place. So I'm going to multiply each of these guys by 2 when I add them together. And when I do that, this, let's see, because there are 2 of them, both of those cancel with one set of these. And then NO3 cancels with one of them. NO cancels. And you end up with 2 times N2O5 goes to NO2 plus NO2 plus 2 NO2 plus O2. So 2 N2O5s go to 4 NO2s plus O2. So that's the overall stoichiometry of the reaction that this proposed mechanism is being used to try to understand. So in B, it just asks you what are the intermediates. Intermediates are things that are formed, but then they're also consumed. So we have NO being formed, but also being consumed. And we have NO being formed and also consumed. So both of those are intermediates in this reaction. They're not something that you put in or that you'll take out as a product. Then the next thing they ask you is this mechanism, what is the rate law for this mechanism consistent with the experimental rate law? So they said in the beginning of the problem that the experimental rate law showed it to be first order with respect to the dinitrogen pentaoxide. So this would be the experimental rate law. And when I look at this mechanism, remember you take the rate from the slow step, so that's the second step. So rate would equal K2 times NO2 times NO3. We can take the rate law essentially right from that step of the mechanism. It's not like an overall reaction where you can't use the stoichiometry. This step is saying this has to hit this, and when it does, things fall apart to make these 3 species. Whereas when you look at this, it's not saying that 2 of these have to collide. So there's a huge difference between a step in the mechanism and the overall reaction. So I use the slow rate determining as the same thing. So if I say it's slow, it determines the rate. And what you notice immediately is that one of your intermediates is part of your rate. And that just doesn't make sense because you'll never know the concentration. So you would like to get rid of that intermediate and have its concentration in terms of products and reactants. So if we look at the first step, it says it's fast and reversible. That means this is essentially always staying in equilibrium, which will be the focus of the entire rest of the class. But at this point, trust me when I say that if this is really fast and this is really slow, this is always staying in equilibrium so that the rate forward always equals the rate backwards. So if I write the rate forward for step 1, it's K1 times the reactant. And the backwards reaction would be K minus 1. And now each of these would be a reactant if it's reacting backwards. So the rate forward equals the rate backwards. If I rearrange that and solve for the NO3, so just take everything to the other side, I end up with this expression. And then I can easily take this expression and plug it in for that concentration. And so now we have rate equals K2 times NO2, the first parts. And then I'm going to put in all of this stuff for NO3, K1 over K minus 1, N2O5 over NO2. And when I simplify that, so cross off the NO2 on the top and the bottom, group all the constants together, I end up with K1, K2, K minus 1, which is just a constant, ratio of a bunch of constants, times the concentration of N2O5. Therefore, it is consistent. The theoretical rate law that comes from this mechanism shows that my reaction is first order with respect to N2O5, and so did the experiment. The last thing they ask you is, what's the experimental rate law in terms of rate laws for your individual steps in your mechanism? And so that's just this group of constants here is equal to the experimental rate law, or experimental rate constant. So those are 4 good problems, and you'll have lots more problems in your homework to work on. So that is the end of this session.